Welcome back to Electrochemical Engineering. Today I'm going to talk about batteries, focusing on metrics for efficiency, self-discharge, and cycle life. Below are two figures. One shows the capacity of various battery chemistries, lithium iron phosphide, lithium nickel manganese cobalt, and nickel cobalt aluminum oxide cathodes as a function of cycling. You can see some degrade much faster than others. We'll talk about why this might be and how to understand these types of measurements. On the right, this is a so-called silicon anode. Silicon has a very high capacity for lithium. It makes a lithium silicide alloy upon charging, but there was much development needed to get this silicon anode to work, and commercialized systems are typically variants of silicon carbon type. You can see here plotting something called the Coulomb efficiency. This is how many electrons go in versus how many electrons go out. If the electrons don't come back out of your battery, that means they're undergoing an internal chemical reaction. Below is how the capacity changes with cycle number. This tells you the total number of electrons you can put in or out per gram of material. So let's define these things more quantitatively. Eta coulomb, coulombic efficiency, is the number of coulombs of charge that's extracted from the battery on discharge, divided by the number of coulombs that you put into the battery on charge. If the electrons don't come out, they must be doing some sort of detrimental internal Faradaic irreversible reactions. For example, growth of a solid electrode interface, evolving gas, for example, hydrogen and oxygen evolution in a lead acid battery, or making dendrites that grow and detach from the electrodes, and other irreversible deposition processes. Overcharging also lowers the Coulombic efficiency. What is overcharging? Overcharging is driving the battery to a higher potential than the highest reversible redox transition in the electrode. For example, consider a lead acid battery on a charger overnight. Side reactions occur when trying to put too many coulombs into the systems. What are these side reactions? You might think about that. A lead acid battery operates in concentrated sulfuric acid. So what other electrode reactions can you drive? Well, you can split water into hydrogen oxygen, and those reactions are irreversible. We can also define the voltage efficiency. The voltage efficiency, eta V, is simply the discharge voltage of the cell on average over the charging voltage of. Typically, you have to put a higher voltage in to charge the cell because you have to pay those overpotential penalties to drive the Faradaic and transport process. You have to drive those same processes when you discharge the cell, but now the current's flowing in the opposite direction, and those overpotentials are opposite in sign. So you never get the full voltage out of the cell that you put in. This is a major component of the energy efficiency, the round-trip energy efficiency of a battery. If we integrate over the entire discharge time, TD, we can get the average voltage of discharge from the cell. It's the integral of V of t dt from 0 to time TD divided by, and there's an error in the book. This should not be I, this should be 1. If it was I, then you'd have the average power. I times V is power. We can then calculate the energy efficiency. It's the product of the coulombic and voltage. The voltage efficiency is on average how much voltage is the cell producing during the charge-discharge cycle. It's the fraction of the free energy, but if you don't get all the electrons out, you have to account for that too. So this is the fraction of the free energy and the voltage that comes out, and this is the fraction of the electrons that make it back. The product of those two gives you energy out over energy in. This is called the round-trip efficiency. It's typically around 90% for rechargeable lithium-ion batteries cycled at reasonable rates. How would you get round-trip efficiency from the data at the right? Why don't you stop your video and think about how you might extract that data from this lithium iron phosphate battery cycling response. Now let's talk about self-discharge mechanisms in batteries. In any battery, there's an internal current that is flowing, that is discharging the anode and cathode. The self-discharge current is given by the total cell voltage divided by the resistance of any shunt or short pathways internal to the cell. This is something you don't want to happen. Any pathway that carries electrical charge between charged electrodes internally, i.e., so the electrons don't have to go through the external circuit where they do work, is a self-discharge. The simplest is a short or an electrical path between electrodes. It can be caused by, for example, mechanical shock, volume changes during operation, or dendrites. A few years ago, there was a lot of news about the Galaxy Note 7 causing dramatic fires, and they got banned from airplanes due to internal shorts releasing substantial amounts of heat and blowing up these batteries, causing them to catch fire and be quite dangerous. The challenge is self-discharge rates typically increase as the temperature increases. So there can be an autocatalytic thermal runaway, whereas as the current starts passing internal to the cell, which you have no way to shut off, the temperature starts increasing and more current passes and you have an explosion. Now, self-discharge rates, even in state-of-the-art batteries, vary substantially. Nickel metal hydride, that's an aqueous battery technology, relatively low voltage, below 2 volts. It's about 30% per month. Lithium ion battery, state-of-the-art batteries, less than 5% per month. And then these lithium primary cells, which are non-rechargeable, can be as low as 1%. What are some mechanisms of self-discharge? One is called the shuttle mechanism. So anytime I have, say, 2 electrodes, and you know this from advanced electrochemistry, I can take a reduced form of the couple, oxidize it at a positive or anode electrode, and then that thing can diffuse to the other side of the cell where it can get reduced at the cathode, which can diffuse back to the anode. This cycle acts as a carrier for electronic current from the positive to negative electrode. This discharges the battery. One example is the breakdown of the polyamide separators in NiCad or nickel metal hydride now cells to form ammonium hydroxide impurities. For example, ammonium hydroxide can react with the NiOOH, the nickel oxyhydroxide. This is the charged form at the positive electrode to yield the discharged electrode and NO2-. Nitrite, NO2-, can diffuse to the negative electrode where it reacts to reform ammonium hydroxide and discharge the metal hydride. These two reactions combine to yield the discharge reaction of the battery. So this is a catalytic redox process that can run without current going external through the cell. Such reactions often can also occur with metal impurities. For example, iron, where you can have iron or other soluble metals shuttling between different redox states and carrying electric charge across the cell. These take energy, resistively heating the cell, but don't give us any external. Another self-discharge mechanism is corrosion. This can happen because of the thermodynamic instability at one or both electrodes. So let's consider the lead-acid battery. For example, in a lead-acid battery, lead oxide at the positive electrode is supported on a grid of lead. H2 evolution at the negative electrode can corrode the cell according to the following reaction. Lead at the negative electrode can drive hydrogen, can make hydrogen and lead to lead sulfate. Lead at the positive electrode can react with lead oxide to make lead sulfate. So here you have lead in 0 valence state reacting with lead in the +4 valence state to go to lead 2+. And at the negative electrode, you make hydrogen and you use electrons in lead to do that to make lead 2+. So this is a purely internal reaction. You don't need to move electrons externally through the cell to do that. The other thing that happens with batteries is the capacity typically decreases as you cycle the cell. We call this fade, capacity. This can be due to irreversible self-discharge, and we typically assign the capacity fade in batteries to both cycle life and calendar life. Cycle life is fade that occurs to cycling the battery. Calendar life is fade that occurs to simply the battery getting old. So mechanisms that degrade the ability of the battery to hold charge and release that charge due to changes that happen in the absence of cycling charge in and out of the battery. There are many mechanisms that lead to capacity fade, and this is still an active area of study, both R&D laboratories at companies and academia. It can be due to the loss of active material. It can be due to larger polarization from increased charge transfer resistance or internal resistance due to changes in the surface of the particles that hold the charge. It can be due to chemical shorts, redox shuttling, building up of that redox shuttle concentration with time, leading to increases in self-discharge. One thing to think about, you could do this as a thought exercise, is how would you determine how each of these affects the capacity fade in a given cell? How do you tell the difference between charge transfer resistance, loss of active material, chemical shorts due to redox, shuttling, and self-discharge. Can you think of a series of experiments that would help you understand this? This is something we can talk about in class. Here's some data for a typical lithium-ion cell circa 2015. You can see as a function of the number of cycles, the capacity degrades from about 5 amp hours over about 800 cycles to less than 4 amp hours. And typically, the cycle life is where the battery has about 80% of its initial capacity. That depends a lot on the application. Capacity fade also depends significantly on the depth of discharge. What does depth of discharge mean? That's how much of the energy you take out of the battery. It's different if you pull all the energy stored in the battery out, you discharge it so it has no energy left, versus only discharging it half the way. The reason is because as you discharge a battery completely, the volume changes and expansions and potentials are much more extreme than if you only discharge it partially. Similarly, when you charge a battery completely, the volume changes and potentials are much more extreme than when you also charge a battery only partially. This is why in, for example, a Tesla, you almost never charge above 90% state of charge unless you're planning on going on a very long distance trip, because this degrades your battery much faster. That's one of the ways they make the Tesla batteries last longer, is they have a very active battery management system that keeps the battery operating under conditions that are conducive to long life. This also tells you shouldn't let your phone completely run out of charge before charging it, and you should stop charging your phone before it reaches 100%, around 90%. Of course, phone manufacturers don't, I think on purpose, include built-in software to allow you to control these charging behaviors in order for your battery to die and you will buy a new phone sooner. One of the reasons capacity fades with cycling has to do with these volume expansions. You've seen a lot of this examples in real life. Imagine I have particles, here rocks, for example, in a mountain stream, Pacific Northwest, and those rocks have water intercalated into all the pores and cracks in the rocks. Okay? And when the volume of that water increases, when it freezes, it actually expands the crack a little bit. It melts, and the ice comes out, and new water fills the crack. And there's a little bit more water now because the crack's bigger, and then it expands again. And it melts and flows out, and this cycle repeats until you can actually break apart very strong bonds due to these expansion contraction cycling. This is called ice wedging in rocks, but it's the same idea that can happen in battery electrodes. And understanding this is very important. In fact, Lin-Chin Mu, our research professor here at the Oregon Center for Electrochemistry, is an expert in controlling these processes in high capacity cathode materials for lithium-ion batteries. I want to end now with a discussion of some data from Jeff Dawn's group. Here he's looking at commercial 18650 format lithium-ion battery cells with different nominal capacities due to the different battery chemistries. So lithium iron phosphate, nickel cobalt aluminum, nickel manganese cobalt. So these are different oxide alloys that have very different properties. You'll notice that the lithium iron phosphate has by far the lowest capacity. Amp hours in this particular battery has the lowest ability to store charge per volume and per mass of this cathode material, and that affects the battery substantially. Its voltage is also a bit lower than the other, but if you look at its performance, whether you discharge it and charge it between 40 and 60% state of charge, 20 and 80% state of charge, or 0 and 100% state of charge, the rate of loss of capacity is relatively similar. And the total loss in capacity is small, less than 10% over 3,000 cycles. So lithium iron phosphate battery chemistry is actually very good for many charge-discharge cycles. And it also has low cost because it doesn't have the more expensive nickel and cobalt cations at the cathode. But for EVs, typically you care a lot about how big your battery is. You can see that these higher energy density NCA and NMC chemistries hold a lot more charge for the same size battery, the same 18650 cell, remember 18 millimeters diameter, 65 millimeters length, cylindrical format. And so you might use these in a high-end Tesla, and you might use one of these lithium iron phosphate batteries in a less expensive car that allows you to drive a shorter distance. These cells, though, they tend to degrade much faster. So look at the NCA chemistry. The NCA chemistry here has a fairly high voltage, and it has a high capacity, the highest capacity, and it degrades the fastest. It degrades over only 500 cycles, loses 20% of its initial capacity. The NMC is a little bit better, has a little bit lower capacity. So the fundamental challenge in a lot of battery chemistry is understanding how to control all these processes at various length scales, the interfaces, the volume expansion, the formation of SEI layers. We'll talk a little bit more about that soon. So that when the battery cycles, you don't lose capacity, you don't lose voltage, you don't increase self-discharge rate, and you can get these very high capacity batteries to last for thousands and thousands and thousands of cycles. That makes the average cost of putting electrons in and out of a battery dramatically lower if you increase this. So that's all I have for you today. I look forward to talking to you more about this and these concepts in class.